So actually, our next topic, actually, I want to talk about this numerical solutions of ordinary differential equations, because we have talked previously the solution of first we have talked about algebraic equations, then we have talked about this actually uh, uh, nonlinear equations, and after that you have that ordinary differential equations. So we have to think about how to solve them actually. So then equations, first the people do some classifications also, whether it is homogeneous or non-homogeneous, but all equations can be solved no matter whether they are homogeneous or non-homogeneous. So homogeneous equation is something like that. If any equations, any ordinary equations can be rewritten in this. Let's say you have this f, uh, a function, and then you have a dy upon dx, and if you can write this into this format again as gx, and if you have two functions, one is g, one is x, and of the same degree, and then this ordinary differential equations is being treated as a homogeneous. So these are easy to solve actually, just only like that. So here you can write y equal to ux, and then you may get this type of function, that a function which is for completely a function of u. So this side you have u, so you have one variable there, so you can easily integrate, right? So that's the easy to solve actually homogeneous equations, you can say, compared to the non-homogeneous one. So you can do sometimes separation of variables, and then you can integrate it. So that's what is some actually examples, means some another the definitions here. Differential equations are homogeneous if it is homogeneous functions of unknown functions and its derivative actually. So here then you have another things here. So one thing is there are no constant terms, so that is also treated as a homogeneous equations. Then here you have means another definitions here, say linear ordinary equations of any order may be reduced by integrations form to solution of homogeneous equations by removing the constant terms. So this is just a small definitions of homogeneous equations. Now to solve the ODEs, so first method is being developed is your Euler's method, and this can be derived from your Taylor series expansion. If you are calculating functions, and then you have so many derivatives, and if you are just considering up to first derivative only, so you will end up with this one only. So here you are calculating here a new value of function with old value. You are multiplying by step size and function value at the previous values which are given to you. So this method is called a initial value methods. Here you should know what your function values. This is a function value actually fn minus 1. You should know that, corresponding to x0. You should know this actually. Okay, and this is a given function. You are calculating a given values x naught and y naught. So these are the initial value problems, that you know that what should be your value of y corresponding to value of x in the beginning. So that's called initial value. You know in the beginning everything. You know what should be your function value or your variable y. Let's say you are solving it for y, which is a function of x and y. So you know that what is value of y at x equal to 0. So that's called initial value problem. One thing is that if you see here, this side is yn plus 1, means new value of y at another step size where you have moved to x naught plus h. You know the value at x naught. Now you are calculating value at x naught plus h. So this is how it would be calculated. You know the value of y naught. So substitute here, multiply by plus h, multiply by function value at previous values of x and y naught. So you will calculate this. Now you see this side you have yn, this side nowhere you don't have yn. So it's completely explicit method here. So by taking your initial values, it will start calculating and it will not stop. So this is some sort of, you can say, a self-starter type of the methods. If you know initial values, you can. Now what about this step size? So step size is practically in our hand. As you will go to a larger step size, you are bound to get more number of errors, because this is just a approximation from Taylor series. You have neglected other higher order term, considering that your h is small. So h is small means it should be practically small. It's not in terms of words only that we have just say h is small. No. So it should be small enough so that your h squared term of second order derivatives in your Taylor series expansion should become negligible actually. So this h is only a governing factors, and what should be value of h? It is practically being governed by this actually, the truncation error, where we want to stop our calculation. So truncation error is being defined the difference between analytical derivatives, that you are calculating derivative value from the analytical formula. One you have calculated from here, and now you are choosing that this much difference is acceptable for you, because the numerical value will not give the correct value as the analytical one. So that difference you are fixing, just like in a pressure drop thing, or you finding the root, you are fixing it. This is the function value I am treating as a root. Practically this must be 0. So that 0 minus of that function value, absolute value of that, is called truncation error actually. You are terminating your calculation at that particular point. Fine. Okay. So here you know if you know the initial conditions, rest of the things can be calculated. So this is one step explicit method actually. Hello, is that fine?
Yes, sir.
Yes, sir.
Okay. The another methods that slightly modified of the previous one is modified Euler's method. So first it is calculating this. This is from the Euler's method you have calculated from previously. So now this is being used just to substitute a corrected value here, and then you are calculating here and repeating it till this yc would become stable, corresponding to the first point here n actually. So you will calculate it again, you will substitute it back here, so you will get here a corrected value here. So this is a predicted value by the Euler's method and a corrected method here, and this would be your value corresponding to yn. So this you can substitute here back again and do it one or two trials so that this value should not change. So that is the final value at this particular iteration. Let's say you are calculating uh, y at point 1 and you know at point 0, 0 पे आपको पास value था, you are calculating at point 1. So you calculated this first corresponding to point 1. So because you are added h equal to point 1, if you are the step size just point 1, calculate it from here, substitute here, you will calculate this again, whatever is being calculated by substitute back here again, and just keep on doing it till this become stable actually, and that is the your final value at point 1 actually. Okay, or each step you have to iterate it actually. So this is two-step explicit method, stable one, and only the truncation error as we have talked about the previous one. Your h will actually fix up the value of it. H actually, the what is the termination point you are fixing, that would be step size. Somewhere we don't know this, so people are changing your h, decreasing it, and now you are changing at what value my answer is not getting changed. Obviously, your answer will get changed for each value of h, no matter how much would they change, 10 to the power minus 10 or 10 to the power minus 14 or 15. After that, your MATLAB, or depending on your computational package, it will say that your answers are same. So you cannot go for that. So you have to define your own function error. Fine, your truncation error actually. Okay.
Yes, sir.
So another method means the before that you should understand that the differential equations are two types. One is just a ordinary differential equations. In ordinary also you have one word is stiff and other is non-stiff. So stiff differential equations means, let's say you are changing the denominator. Let's say you are solving it dy upon dx equal to something. So let's say you have changed dx by a small value. If y is getting changed very drastically, so those type of equations is called stiff differential equations. Slight change in your numerator or your dependent variables actually, independent variables. Your dependent variable is changing too much actually. So those called stiff differential equation. In that case, your step size must be very very small, because if you will just miss it, you will miss a lot of informations, because the function is varying very abruptly and you have missed that particular zone actually. Just I can draw a one slide to you so that you can understand what do I mean to say. So insert, let's say, with the same, yeah, this one. Let's say this type of function you have here, and now this is your, sorry, I can draw the line actually. So this is your x variable, and let's say this is your function. So let's see, if you would change very fast change between this point to this point, you will miss all these particular points. Because here, if you see the variation between, so if you will just vertically make them upward here, is, let's say this is another point here, and this is another point here. Okay, so suppose you have this, there's the huge change in function here. You see that between these two, this is the change. So if you are changing this step size here, you will directly getting here. You are not able to capture this. So to capture this profile, you have to have a step size somewhere, many step size here. Only then you can reach here, right? Otherwise, you will miss this particular trend. Same thing for this side. Let's say here. So if your profile is just like that and your step size is more than that, you will reach somewhere here. So your behavior is not this. Your behavior would become something like that. Your behavior, because from here you are directly reaching to this. So your behavior is this, which is not true. Your function is something like that. Correct? So in case of stiff differential equation thing, so this is the variation of the stiff, the slight change in x, the huge change in function value. Function value is changed nearly here 4 to 5 times here, from here to here, right? Yes or no? Hello?
Yes, sir.
Yes, sir.
So in that case, you have to take very small step size, and therefore your computational power will go up, right? Because as you will decrease your the step size, you have to put more and more computational power, more and more number of iterations, but you can compensate it. You can compensate it, and then sometimes if your function value is very very large, and it is somewhere in the denominator, it will become a ill conditioned matrix. That function value become too much large actually. So sometimes that explicit techniques also fail. Okay, But implicit techniques are always stable, so therefore those are used for stiff differential equations. Now the another method here for explicit category, fourth order Adams Baseford scheme. So what does it have? This is given that if you know the value of yn, yn plus 1 can be calculated by this correlations 23 fn plus 16 fn plus 1. So these, what does it need? This will start from n equal to 2, because the time you will put the 2 you will get 0, you get 3. So you are getting f0, you are getting f3, you are getting here f2. F1 is not there. Yes or no?
Yes, sir.
Correct? So for that, this this particular method will not start its own. It needs f1 from somewhere. Correct or not? So for that, these methods are not self-started category. So for initial values also, they need f1 value. It need f1 also just to start. Beyond that, it need a value of f2. It need a value of f3. Correct? And f0. So it need 4 values just to start it. At least 3 values. You need 2, you need 3, you need 0. F1, okay, you can calculate from some other technique, but at least you need 2, 3 and 0 values. So these values would be calculated by your Euler's method, or maybe from modified Euler's one. So these is multi-step methods, but these are not a self-started one. They need some, they depend on some other, mean the method. So best one is the Euler's method, that is easy to calculate. So what would happen here? You would have some errors in first 3 terms. After that, you can compensate. You can are getting a final way, because multi-step methods gives much more correct means derivative values or function value as compared to the single step methods actually. Okay, and completely explicit here, because here yn plus 1 is not being involved this particular side here. So this completely explicit method here. So whatever is present here on the left hand side, if it is not present on the right hand side, it means you are fine here. Okay,
Yes, sir.
Yes, sir.
fine. So it cannot also use your sharp change also, so it's not the suitable for stiff differential equations. The another method is fifth order of the Adams Baseford. This is again a multi-step mean the method here. So this also is being calculated by this. So you have h upon 24. This is the formula. This derivation is there, so we are not interested in that. We want to use it actually directly. What does it need again? This need fn n minus 1, and so practically it will start from the minimum value is n equal to 3. So if we put n equal to 3, it will become 0, it will become 1, it will become 2, and it will become 3 here, right? So these you need 4 function values in the beginning just to start it. Only then you can calculate n equal to 4 actually. Okay.
Yes, sir.
Yes, sir.
Now one more scheme is here, Adams Moulton schemes here. So here one you have a predictor method here. So this predictor would be calculated by this, and a corrector here. So corrector would be calculated by this. So this is again a implicit scheme here, because here whatever is being calculated would be substituted here somewhere just to calculate fn plus 1, and then whatever is calculated again substituted back to get a stable value. So this fn plus 1 is coming from here only. Okay, so this is a implicit scheme actually. Now you might have heard the term a Runge-Kutta methods there. So this is a family of the methods So the previous one you have multi steps here. You see here you have to need one, two, three, four function value just to start it. Previous one also four, then three, right? So you need these many function values to start it. But in Runge-Kutta method, you don't need those many. You just need one, and rest of the things would be taken care here. So here you need this, so you have to just generate them precisely actually. So Runge-Kutta also can serve the same purpose. Only thing you have to is require more steps just to calculate, just like your Euler's method. Euler's method is also a Runge-Kutta method only, that is of first order. It can give you the correct answer. Only thing you have to need more and more steps actually just to compensate your explicit, I mean the stiff differential equations and all this, right? So being classified here, you have here explicit, semi-implicit, and in the implicit, you have all these category in Runge-Kutta methods. And implicit schemes are not set for non-linear algebraic equations, and you can solve it for stiff differential equations. So let's see what Runge-Kutta methods are. First order Runge-Kutta method is your Euler's method, which we have talked just now. Second order Runge-Kutta methods is modified Euler's actually, which we have talked also. And then we have a third order one, Runge-Kutta method, third order, which is also known as Runge's method. So here you have to calculate several terms here. First you are calculating K1, so being calculated by step size h, multiply by your function value your at initial conditions, which is at n minus 1. Practically you are calculating x naught and y naught. If it is a function of x naught or y naught only. If your differential equation is function of x and y, you are calculating at x naught and y naught. So that particular term or that particular step is known as n minus 1 step actually. Okay, so then you are calculating K2 by this particular expression, then you are calculating K prime by this expression, then K3 from here. After that, you are calculating K, that 1 by 6, K1 plus 4K2 plus K3, and then you are calculating Y1, your first value of Y1. You know the Y naught, and now you are calculating Y1. So Y1 is Y naught plus K. K would be calculated from here. Now general expression in terms of yn is given yn minus 1 plus k. So n would start from here, practically from 1. So if you will put a 1 here, you are calculating y1, it will become y0. Okay. So this is your Runge's method. Hello.
Yes, sir.
Okay, sir.
So this is third order Runge-Kutta method. Actually, let me correct it. This is something wrong. Next is fourth order Runge-Kutta method. So that's practically you are known as a Runge-Kutta method only. This is actually fourth order. Previous to, you know, with those names only, Euler's method, modified Euler's, Runge's method, you know only this as a Runge-Kutta method. Yes or no? Have you heard these terms earlier?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
So here what you have here, so you are calculating this here from here. So you are calculating a K1 here, then you are calculating K2, then you are calculating K prime, then you are calculating K3 here. Now you are adding, I think that I did some mistake here. You should have K1, K2, K3 and K4. Is it fine? Let me see. Third order.
The third order and fourth order formulas are same.
Yeah.
So
So
there should be one K4, I think.
yeah,
Yes.
K4 should be there. That's what I am also recalling that. So let me correct it. 1 minute. So for that, this is half of k1 is fine. Let me correct it. Actually, I corrected. I forgot to save actually. So यहाँ तो दिख रहा है, उधर कहाँ गया? Equation. You can see here, right? K3 is h1 by 2, the half of k2. That's fine. Then you have this is k4. Okay. You have h of x plus h. Why not? This is your k3. Then after that is k 1 by 6 k1 k2 plus 2 k3 plus k4. Is it visible now?
Yes, sir.
Okay, so I just corrected it here. So now it is fine, I think. So this is your fourth order Runge-Kutta, properly known as generally known as the Runge-Kutta methods only. So you are calculating here K1. So this is H practically F naught. So you are calculating K2 again H practically X naught plus 1 by 2 of H and Y naught plus this half of K1. Then you are calculating K3 that X naught plus half of H plus half of K2. Then you are calculating K4 X naught plus H Y naught plus K3 actually, right? So you are getting a final K 1 by 6 K2 K2 plus 2 K3 plus K4, and then you are calculating the Y. So this is again also a multi-step method, but all of them comes in the self-started category actually. They will start from an initial value. So if you know the initial values, you can solve them. Okay.
Yes, sir.
Now another
Yes, sir.
method is MILNE'S method. So that's again need to be. This is also again a multi-step methods here. So first is you need y1, y2, y3. Uh, have you heard the term Picard's method?
Yes, sir.
What is that?
Yes, sir.
What is that? किसी को याद है? So you need to have y1, y2, y3. Either you calculate for Picard method or Taylor series method or Euler's method. Fine. So you will calculate that. Once you have calculated, after that you need a function values corresponding to x naught by naught, corresponding to your corresponding y1. So you corresponding x would be x naught plus h. Then y2 x naught plus 2h, then y3 at x naught plus 3h, and y3. You got these three function values. Practically four, right? You have f naught, f1, f2, f3. Once you know these, you can calculate your predicted methods is this y4, y this, y naught, 4h, y3, 2f1 minus f2 plus 2f3. Then you can calculate f4 corresponding to y4 by this. Now a corrected value would be this y2 plus h y3, f2 plus 4f3 plus 4f4. Now you got here f4. First you will substitute this by predicted here. You will get f4. You will this. You will calculate yc. Now this yc again substituted back into f4, and you will get y4 the again put. So there would be a loop between this f4 and yc actually, and then you will keep on moving till you will get a stable value of y4. Okay, and that would be the value of your y4. So that's what you have here. Now you want to calculate same way is value of y5. Y5 is this from here. So expression for this is y1, 4h by 3, 2f2 minus 4f3 plus 2f4. Y5 is being calculated by this f5, sorry. So now from here corrected value is this y5 actually by subtracting this. Again there would be a loop between f5 and y5c, and you will run it till it becomes stable actually. So from here you just calculate two new values. You calculated what two new values? A y4 and a y5. Two new values you have calculated. Three you already have, y1, y2, y3. Now you will uh, l- change your y1 y y3, y2 y y4, and y3 y y5. Repeat the steps actually same thing, and again you will get now the you will get two new values. What are the two new values you will get now? 6 and 7, right? And that way you will keep on continue, and that would also be the one of the method actually just to calculate. And so far we have just talked about the methods, that these are the various methods. Most of them you already know. Only thing I might have told you this Milne's method and Adams methods, only these are the new one to you, right? Rest of the methods you already know, correct?
Yes, sir.
Now this is the problem we want to practice it here. So this is a simple equation. First we want to start with this. So dc upon dt is given by t plus c. Initial conditions are given to you, that c equal to 1 at t equal to 0, and you are supposed to calculate the value of c at t equal to 1. So you can use first your Euler's methods and just take a step size, and let's see what is coming. Or again your step size is, as you see, it depends what step size can give you a perfect answer. What would be the perfect answer? Because this equation I have willingly taken in such a way because it can be analytically solved by you easily, right? So first thing, you solve it analytically. What is the analytical solution of that? Then you solve by these methods, and then you check in each method what should be corresponding step size so that your answer should overlap with the analytical one if it's possible. In some case it may not be possible no matter what step size you are giving. This is also possible. So you are forced to give a truncation error actually. So that only you will come to know with the help of this. And first you solve it. इसको एनालिटिकली सॉल्व करिए जरा, क्या आता है, लेट्स डू दैट. Just find its analytical expression first. What would be its analytical expression? Are you solving?
Yes, sir.
हाँ करिए.